Good morning, everyone. Good morning from Oman. We are just beginning the session. It's already 10 a.m. here. Welcome to the Oman Petroleum and Energy Show webinar on Enhanced Evaporation by EcoMister Evaporator. The webinar will be presented by Sean Baudreau, the Division Manager of EcoMister Evaporator. EcoMister Evaporator is a flexible and affordable solution for wastewater evaporation developed in Canada and represented by our exhibitor Ras Al Hamra in Oman. In our session today, we will discuss the theory of evaporation, disposable volumes and costs, customer success, evaluating an evaporator, followed by the question answer session. Over to you, Sean.
Thank you, Pooja. Appreciate the introduction. Thank you, everybody, for joining. Appreciate the opportunity to present. Looking forward to sharing some information on enhanced evaporation. For many, it might be something that you're aware of. Others, it might be something that's completely new. Really would like to go through the presentation and offer some question and answers session at the end. So if you have some questions, please feel free to post them or hold them to the end. Post them in the chat or hold them to the end, and we can go through some question and answer at the end if there's anything on the presentation or anything else, or we can follow up afterwards. So without further ado, I'll jump right into the presentation. My name is Sean Baudreau. I'm the Division Manager of EcoMister Evaporators. We're based here in Western Canada. We sell this solution all over the world. We've been in business for over 25 years in this evaporator division. The company's been around since 1990. And looking forward to sharing some more information here. So as Pooja indicated, we'll go through a bit of a technical presentation on the theory of evaporation, talking about disposal costs and volumes. We'll go through a bit of some case studies and customer successes, and then talk about evaluating an evaporator, and then we'll go through some Q&A. So the theory behind enhanced evaporation. This is something that is important to how we designed our solution, and it talks about really some of the science behind it and the practicality of the system. So common sense dictates you can accelerate evaporation by creating more surface area for the water in the form of water droplets in the air. Increased evaporation will occur as more air is allowed to surround each individual droplet. So really what we're saying here is we're trying to create an optimal environment for evaporation. Natural evaporation occurs all over the world every day. And what our solution is doing is we're trying to create an optimal environment for evaporation, and specifically for wastewater disposal. And this is one of the key aspects of our theory that we follow. Hang time. Hang time is the amount of time a water droplet is suspended in the airstream. So really what we're doing here is we're launching droplets into the air, and we're giving them this optimal environment for evaporation. We're supercharging the evaporation process of a natural evaporation pond or containment pond or effluent pond. And we're doing so by creating this hang time. And that's why we're launching these droplets up over the pond. A couple points on the hang time is we create hang time with a turbine-based fan, and we inject water droplets into this air column that we create here. The idea behind the system is we're actually creating droplets that will carry the contaminants, allow the heavier solids to precipitate back into the pond, and again, carry the contaminants as they fall back into the pond. An important note here, and why I have this droplet here, droplet containment, this is the idea that we're trying to follow as we create these droplets. We're not trying to dry aerosol or evaporate the entire droplet. We're actually trying to reduce the size on every pass and create this recirculating load over the pond, or the effluent pond, or the containment pond, and basically reduce the volume of water in that pond by recirculating the water over top. So again, trying to get rid of the water while managing the contaminants inside of that water is critical. The hang time, in order to give us effective hang time, we have to be launching these droplets high enough, far enough to get reduction. And it's generally accepted that evaporation is affected by humidity, temperature, and wind conditions. The greater the temperature, the less the humidity, and the greater the wind conditions, the greater the amount of evaporation. And we have accepted these facts as truths in our design, and this is how we follow the principles for our hang time. As we dive into a bit more of the science, the evaporation is depicted, and the efficiency of the evaporation is depicted by the size of the droplet that we can create. So as you can imagine, looking at this table, and we could create droplets as small as 20 microns, 50 or 20 microns, but they get very hard to control. And when we're spraying wastewater and effluent up into the air, we want to be able to control these droplets. So we're actually looking to create larger droplets that we can control. We use wind speed and wind direction controls, automation on the systems to actually also manage drift and manage any of that those concerns as the system is running. And so our goal and the design of every system is to contain everything inside of that containment pond or effluent pond. And we're doing this by simplistically creating droplets that are optimal for control for that site. And we can actually have full automation where we can live control droplets. So we can actually live adjust droplet size based on controlling pressures running pressure on the pump and changing the droplet size live to adjust to atmospheric and local climate conditions. But this is a simplistic example of how we're trying to create droplets that are large enough to be controlled, but small enough that they're going to get good evaporation efficiency and achieve the hang time we require for that efficiency. Designing an evaporator. So a lot of common questions or common comments come up. You're a snowmaker. Now, maybe this isn't so common in Oman and in the Middle East in general, but the idea is a little different. So a snowmaker is actually designed to coagulate water droplets and have them coalesce and form and basically fall. If it's cold, if the air temperature is cold enough, it'll create snow, and it will fall back to the earth as snow. So we're trying to, in that sense, they're trying to create bigger droplets that will fall back and create snow. It's kind of the opposite of evaporation. We're actually trying to have the droplets not touch each other, not coalesce, and each droplet have its own air path and airspace so that the air can surround the droplet and it can reduce its size, therefore increasing the evaporation rates. So there's, it's a nuanced point, but it's something that is a differentiator, and it's part of the patented design of our technology as we create a laminar flow, which creates more efficient evaporation and really boils down to, the dollars and cents of running the system and being more efficient means that you're getting better bang for your buck on disposal costs. Which leads us to our next point, disposal volumes and costs. So why does all of this matter? Why do we care about, this design and this type of enhanced evaporation? Because really what it translates to is cost-effective wastewater disposal. One HD30, which is the largest model that we produce, will move about 115,000 gallons a day, or over 42 million gallons per year. That's equivalent to 2,700 barrels or a million barrels a year, 2,700 barrels a day or a million barrels a year, and we can evaporate it at a 50% rate. You're going to evaporate, half of that, 21 million gallons per year, at an average disposal cost of less than 0.2 of a penny per gallon. So you'd be hard-pressed to find technology that will dispose of water more cost effectively than that, other than maybe just discharging it without any treatment, which is typically not allowed or not preferred as a methodology of disposal. The efficiency and the evaporation rates, they do vary site by site. We produce estimates based on the local climate conditions. So this is just an example of 50% efficiency rate, which is actually quite good. We don't want to be achieving efficiency rates in the 80-90% range, because then you're actually drying out those droplets too much. You're losing control, and it's not something that is controllable and containable for the technology. So just to give some context, this photo here is a mine site in Australia where they have multiple units running, and so they're able to get, the scalability of the system is quite easy. We're just feeding more water to more units, and it allows you to achieve quite large volumes of disposal per month, per year, just with scalability and control systems that scale with the system as well. So in terms of disposal costs and efficiency, the idea behind this slide here is really to show that, in the MENA region, while efficiency might look low, 50% is, for a motor or another piece of machinery doesn't seem very efficient, and 20% sure doesn't. Actually, those numbers are relative to the amount of water we're actually trying to evaporate and control. And so in a very dry desert climate, 50% efficiency is good, very good. In more humid regions, I'm looking here more kind of towards the Mediterranean area near the water, you're going to get lower efficiency because there's more humidity, typically lower temperatures. The air will not take as much water, but what you can see is you can still get very cost-effective disposal. So this type of technology is so cost-effective that even with low efficiency or perceived low efficiencies, the disposal rates are very low. So it's still something to consider, even if the site might not have what some might say is optimal natural evaporation climates. Like, it doesn't have to be the desert. It doesn't have to be a very dry climate all year. There can be seasonality to it. Where we are in Western Canada, we get great evaporation in the summer and not so good evaporation in the winter because we had a lot of snow. But we can design systems to achieve annual disposal volumes throughout the summer months, while the winter months, maybe do not achieve the same evaporation. But we design the system to accomplish the goal in the shorter evaporation season. So again, that helps with the scaling and how we design each system for each site. Customer success. So I'll run through a few examples of some customers and applications that use this technology to give some color to what we're talking about, and try and maybe I'll show a video here if I can. This customer here is an LNG facility in Arizona, in the U.S. They have a relatively small pond, and they bought a single unit, single basic pumping system. They spent $50,000, and it removed the need for them to install a $500,000 pond as an additional capacity that they were going to need to add. So just in that scenario on its own, they were able to pay that potential cost back quite quickly. The ROI on their investment was very, very quick. This system itself is actually interestingly run in the winter months in Arizona. So they use the system to overcome the evaporation. The natural evaporation season is obviously weaker in Arizona in the winter than it is in the summer. The pond naturally evaporates enough water for them in the summertime, and in the wintertime they use our enhanced evaporator to overcome the poor natural evaporation that occurs in that region in the wintertime. So an interesting application for them. They're using the pond for they produce LNG, and they have byproduct effluent water that comes out of that process, and they're storing it in the pond and evaporating it. So interesting application for them for sure, and probably relevant to some projects and some sites in Oman and in the region there. This is a bit of a larger solution or larger system for one of our customers, Alcoa, in Brazil, in the mining region of Brazil. This site is a little more humid than I would say Arizona, but they're using 3 units. We call this a tri-pack. They've got a pump system that sits over here, and they're running 3 units off of that pump system. This site is actually using a bit of drift fencing to help mitigate any further concerns with their drift. As I noted earlier, the actual controls of the system can be utilized to manage drift on their own, where we would have wind speed and wind direction sensors, and we would run the system. And if the parameters for the site fall outside of our preferred operating specs in terms of wind speed or direction, we simply shut the system off or tune it down to an optimal level to continue running. So a good example with this site here of disposal at a mine in a more humid climate in Brazil. This is a site actually not so far from us. It was one of the earlier development sites in the mining sector for us. The site is currently owned by Barrick Gold, but back in the day it was a company called Homestake, and they had a large tailings facility where this site is at 4,700 feet altitude, so it's got some seasonality to it here in Canada. So we ran the system. It's 50 to 60% humidity. Summer temperatures are in the 70 degree Fahrenheit range. And we were able to run our systems on their tailings pond, and this was at end of life, and we basically removed the water concentration from the pond, and we left it to a state that was able to be remediated, to go bioremediation, and they put cover on and basically reclaimed the tailings facility back to a natural grassland. So we were able to help get rid of that volume of water very cost effectively in a very remote kind of mountainous site. And that's a very good and typical example of where we're utilizing this system, and one of the earlier sites where this technology was used. We've since done testing with the U.S. Bureau of Reclamation in the Salton Sea. We've done testing in the oil sands with Suncor and companies like CNRL. We worked with the U.S. Department of Energy on specific testing as well. So over the years, we continue to test and advance and enhance the technology. And the controls are one thing that's really something that's enabled the systems to be more automated. That's becoming a standard integration into existing facility infrastructure, and running so that the operators in the main control room can see and control and understand what's going on with the technology, because for the most part they just run on their own. They don't really need much interaction at all, and that's the way they've been designed, because for industrial sites, oil and gas sites, mine sites, we don't want people out there babysitting them. We want them to be left and run and do what they're supposed to do, which is pump water and evaporate water. Another site here in Canada, I like talking to this one too, because this customer was trucking. They were doing trucking disposal costs. This is a landfill leachate scenario. But it's similar to any industrial site that's having to truck water off site as an example for an alternative to treating it on site or disposing of it in other ways. They were trucking it and having to pay pretty large trucking costs and disposal costs from their perspective. They bought a unit with a generator as well. They run this off of a generator. We can produce grid power, generator powered units. It doesn't really matter. but they were able to pay that, simple payback on that investment very quickly based on their existing trucking costs. So again, a cost-effective method of disposal. Something that, again, like I talk about the seasonality, this site is very seasonal. They evaporate all of their water. They basically run the system in their spring, our spring here in Canada, and they get a lot of snow melt and runoff water. They're getting rid of that water from the previous winter, and then in the summertime, they start lowering the pond further to prepare for the next winter's snow and fall rain. So they basically are managing their pond levels by, adjusting, by running the system and managing and dropping those levels to take on and increase their capacity for the seasonality of their water flow at the facility. Who else have we worked with, or who else do we support and have over the years? Many companies that are probably quite familiar to all of us, but these are just a handful of some of the groups that are using or have used our technology. Predominantly we're in the mining, oil and gas, power generation sectors. As noted in one of the case studies, we do solid waste as well. We manage landfill leachate at solid waste facilities. We do rural wastewater management. We also help with, other where we can be a complementary solution. This technology can be a complementary solution to treatment facilities that have byproduct water like RO. If RO treatment has a brine solution that comes out of that process, we can be a disposal method for that water. Desalination plants, lots of different applications for the technology. Food processing, as you can see with McCain, fertilizer with Mifco, lots of different applications for the technology. The end result, or the end technology, the end goal of the technology is to remove or dispose of wastewater in a cost-effective way. And the applications are very broad actually for this technology, and it really comes down to tailoring the system and the technology to the site and to the goals of each site, which is something that is easily done and something we support on as well. How do we evaluate an evaporator? We've touched on a few points, and I'll go through some of what we've discussed, and really some things to consider when looking at enhanced evaporation and evaporators. Looking at average water droplet size. As I noted initially in the a bit more of the technical explanation, droplet size is key. It's key because smaller droplets, while they may evaporate faster, is not always the best option when we're dealing with wastewater. As I noted, we don't want to dry aerosol these droplets. We want to be containing contaminants and reducing droplet size through each pass, and basically create this recirculating load. So understanding how what droplet size the systems are producing and how they're being controlled is very key. Hang time achieved by the machine for the average droplet. What is the hang time? Is this part of the design criteria? Are we launching droplets over top of the pond, or are we shooting them back into the pond, just directly down into the pond? I mean, there's going to be different evaporation efficiencies based on that. So it's important to understand if that hang time is part of the design criteria for the system and how that might impact the evaporation rates at your site. Overall cost per gallon, obviously says per gallon, per barrel, per cubic meter. I call this the bang for the buck calculation, right? What is the actual cost input to the result of evaporation out? And really it boils down to, what is the dollars per gallon, dollar per barrel cost of disposal? The largest input into this technology is energy. It's just the energy cost, right? So running the figures, running the numbers for each site, that's going to vary, but really looking at it from a perspective of what is our cost per gallon, cost per barrel disposed, and how does that compare to other alternatives that we might have available to us? That's something that we want to consider. Durability of the unit. I noted this a bit before. Is the system durable and designed for the application that it's being positioned for? Our systems, this technology, we make heavy-duty models. We make light-duty models as well, but we're predominantly making heavy-duty models for wastewater. And what that means is they can handle heavily contaminated water, different sorts of chemicals, pH levels, acidic water, basic water. We can handle all sorts of, we've used these systems in, the oil and gas space. We've used them in fertilizer plants with phosphoric acid, phosphates. There's all sorts of applications that this technology has been used in, and it's important to understand if that technology's durability is amenable to the site and what type of water that's actually being pumped. Flexibility to adjust to conditions. This goes down to our discussion about, the controls that are available, drift control, wind speed, wind direction. We also talk to ease of operation, how easy to operate, how much manual labor do I have to be involved to run it, how automated is the system. Mobility. This photo here shows one of our trailered options that allows you to make a land-based system mobile. We also offer a fully integrated trailer where you don't need to put the land-based unit on a trailer. It actually has its own trailer with its own pumping system. Some sites that's very important where they can mobilize and run the system on different ponds. So something as a feature to evaluate when you're looking at a system for a site for yourself or one of your clients. Reputation and service of the manufacturer. Of course, that's key, in understanding how am I going to service this equipment? Is it made with off-the-shelf components? Of the components that are not off the shelf, how easily available are they? What are the likelihood of them, breaking down? What does my repair schedule look like? That's all key. And I say, from that perspective, we stand behind all of our solutions, and we support from our Canadian head offices, and regionally we have distribution groups and partners around the world to support us as well. Customer satisfaction, and that really boils down to, what are the customers saying? What do the customers say about the success or the performance of the technology on their sites? And so we like to defer that to our customers to share their experience on whether the system has worked for them and how it has. Talking about some differentiators on the technology, there's longevity in the harshest environments. We talked about that on the previous slide. Really, the technology was designed initially for remote mine sites, and these mine sites were in Canada, the U.S., South America, and Central America as well, and really designed to be robust, minimal impact or minimal involvement through manual labor or personnel having to come out and touch and deal with the system, operating 24/7, 365. Best-in-class evaporation, talking about those efficiencies, working to get the best evaporation and the best control of that evaporation for the technology, giving us the lowest costs of the disposal. Continuous improvement through engineering, always working on lean manufacturing, our feedback loops both internally in the production facilities, but also more importantly, I think, from our customers that are out there using the technology. What is working, what needs to be adapted, what can we build on for those different applications and different site conditions. How do we optimize the technology for all the different climate conditions and sites that are out there. Low operating costs and hassle-free maintenance. Again, we talk about that, longevity on the build side. We're building these systems with stainless steel, and then we're powder coating with a 3M product. So we're really building them to handle a lot of different water types, chemical compounds. All the wettable components are stainless steel, and we design it to be low operating costs there's really not a lot of, there's a fan with moving parts, as I'm showing here. You've got to grease the fan bearings. You've got to grease a motor like any electric motor, but you need to do that maybe a handful of times a year at most, depending on your operating hours. And you've got nozzles, and those nozzles can easily be replaced with our quick release cam lock. So those are things that really differentiate us out in the marketplace. And customer support, I put this here purposely with a dash. Our systems we have standard packages, but really they're all tailored for each site, and really optimizing that technology to run both efficiently and meet, not just the disposal goals, but, all the other, tertiary goals and benefits to that site. How do we design the system to address all the needs? And that might be mobility. That might be a need to have the system turn itself on and off. I don't want anybody having to go turn it on. We have systems that basically run themselves. They turn on in the morning and they put themselves to sleep at night, and they turn themselves back on, and they alert the personnel if it's time to maintain the system, or there's a fault that needs to be addressed. So those are some of the things that really stand out and differentiate the technology with others in the field. Where will we see enhanced evaporation? Well, we've talked about it quite a bit, but there's lots of different applications. RO brine disposal, production water. We've got customers that use this technology to deal with production water in the U.S., and they basically are using it to dispose of salty water, salty brine water that comes out of a treated process, and they harvest the salt. So they're taking production water that's treated, and then they're actually harvesting the salt out of that water, and they're selling the salt as an industrial salt product. So that's an interesting application that I think could be used in a lot more areas around the world. Wastewater disposal, just pure wastewater disposal, and that could be for municipal wastewater. Desalination, we talked about. Tailings ponds, of course, with mining. Landfill leachate, stormwater ponds, reclamation projects, site reclamation. We've got a lot of power plants in the U.S. right now, coal power plants specifically, that are being shut down, and they need to reclaim those sites and get rid of some of this water. That's a very common application for us right now. Heap leach pads, heap leach ponds for mining as well, floodwater relief, and there's countless other opportunities to look at. Really, if there's a wastewater or effluent water that needs to be managed on a site, this is a technology that should be looked at as an alternative to, treatment or offsite trucking or deep well injecting, to compare the viability of it on that site and the opportunity for a cost-effective alternative of disposal. And that's my presentation. So I really appreciate the time. Pooja said I would take 30 minutes or so, and here we are 33 minutes in, so that's great. And would love to turn it over to some questions and answers. I see there's been quite a few questions that have come in, and so I'm going to jump over to that application. So here we have a question: how would you compare the turbine approach with fountains within the pond? So that's a really good question. So typically, you might see some evaporator units that have they're basically I would call them sprinkler type or glorified sprinkler units on a pond. They could also be used for some aeration. The turbine approach really boils down to efficiency. The turbine approach that we use is creating a more optimal environment for evaporation. We're accessing, you can imagine, we're accessing drier air higher above the pond. That when you get closer to pond level, like in any lake or body of water, that air right above the surface of the water is quite saturated, right? It's very high humidity. And then as you get above, it starts to disperse and the humidity starts to reduce. And so if we can access that drier air by using a turbine and pushing those droplets up above, we create that hang time we talk about, and we really create a more optimal environment for evaporation, which really just means better efficiency and lower cost per gallon or barrel disposed. So really good question, comparing the different technologies that might be out there. Good question, considering the warm climate in Oman. And again, so we've worked in Oman. We've got lots of different analysis done. We've got customers in Oman. Typically, it ranges between 40 and 50% efficiency is what I've seen based on the evaporation data. How we look at the climate data, we use pan evaporation data is the best data that we can use. Our systems have been designed and tested against that data, and pan evaporation data really gives you a good overall understanding of the local evaporation potential of a site. If that site doesn't have pan evaporation, then we look at regional data, we correlate to a pan evaporation number, and we run estimates on that. And that's where that 40 to 50% number comes from. And I'd say, when you're getting it to 50%, that's great. That's desert climate evaporation rates with this technology. You'll see some other technologies will say, well, we can do 70, 80% evaporation of capacity pumped. Sure, there's potential for that, but you're not controlling your wastewater. You're not controlling your droplets in those scenarios. And so it's important to understand the whole scope of the technology and the whole scope of the needs of the site when looking at that. Question here, do you supply floating type evaporators as fixed type will have issues with wind flow? Yes, of course, we can talk more on that. Our technology that we have, we actually have three options: land-based, trailer-based, or float-based. So any unit that we produce, we actually can float it on the pond. And very good point, with wind flow, there's if you can put the unit on the pond, you can naturally mitigate wind drift or wind flow, as you're saying here. We do it on the land-based units. We do it more with our controls. But if the pond's big enough and you want to float the units and not have those controls or have less, more uptime or availability, that's the alternative, is you float them on the pond, and our systems can do that as well. So yeah, happy to chat further offline as well if there's any more questions about floating evaporators. Good question. So the calculated 2 tenths of a cent per gallon includes just the operation of the OPEX cost of the system. The actual capital cost of the system varies. Depends on the unit itself and if pumping is included and controls. The systems start in the $20,000 range. And for single unit systems, they can go up to $100,000 or more. It really just depends on the dynamic and the configuration. We've had systems where the control system itself is $150,000. It really just depends on what the site needs, but they start as low as $20,000, and the capex is not included in that calculation. Good question about the UK. How would it work? We used to work in the UK with some previous companies. A lot of rain, a lot of humidity. It would work. Yeah, it would work. It would be, as compared to Oman or hotter climates, you would have lower efficiency. But going back to the slide about the efficiency numbers, 20-30% efficiency would still be lower, like low disposal costs in comparison to what alternatives might be out there. And so we just would want to run the feasibility assessment for that site, including what the cost of power is, and and what the disposal goals are. And we run them in humid climates that don't have very hot temperatures. But every site has evaporation. There's always evaporation occurring. And so we can enhance that process and do it in a way that the inputs are low enough. The cost can be very, very very manageable, and the cost can be very competitive and cheaper than most other alternatives that might be out there. Question here about slide 6, droplet diameter. What about the size above 200 microns? Good question. Yeah, there's definitely, you can definitely create larger droplets, larger than 200 microns. The challenge with larger droplets that you might create is you're going to have droplets that will not travel as far and will not get as much hang time. With the mechanical evaporation and the fan running, you can imagine the bigger the droplet, the shorter the throw, which just means lower efficiency. So it's an optimization game, depending on a few site parameters. We may choose to create larger droplets for certain sites, and to control the droplets or manage it. But we also, when I talk about sites that have control, wind speed control, wind direction control, where we can just turn off the system, or we can optimize it to run in those windy conditions, which would mean two things. One, we either turn the fan down and don't throw the droplets as far, or we can actually change the pump pressure and we can actually make bigger droplets, so the droplets don't travel as far as well. So again, different optimization techniques to manage, and that's all doable from an automation perspective. But typical droplets we're trying to create are actually less, they're between 150, 200 microns. %50 efficiency means if we have a 100 cubic meter per hour unit, we achieve 50 cubic meters per hour average evaporation. That's the understanding. So if we have an evaporated X cubic meters, I need to select 2 times the equipment. Yes. So basically that's correct. So the 50% efficiency is based on the capacity of the system. So if you had 100 cubic meters per hour unit, 50% efficiency would be 50 cubic meters per hour, and that's how we scale. We don't design the system off of the capacity or the throughput capacity. We design it off of the evaporation goal. How much water are we trying to get rid of? What is each unit going to evaporate based on the efficiency numbers of that site? And then we recommend the number of units required. How many installations do you have in Oman? We currently have operating a MIFCO. We've had a few installations over the years with some of the energy companies there, but I think a MIFCO right now is the only active installation that's running. The Middle East and the MENA region is an area that we've, I'd say we've serviced over the years, but we haven't actively pursued. And this is part of my objective to discuss and present. We're looking to expand our business in this market with groups like Ras Al Hamra and being a part of the market more directly. So that's my answer to what we have in Oman right now. Good question. Yeah, very good question. What's the typical maintenance cost per year? So the greasing cost is very low per unit. I mean, it's literally, a tube of grease or two. So very, very low on that, just the labor to go out there and grease your motor and grease your bearings when they need them. And then the other wearable component is your nozzles and your nozzle ring. And depending on the unit, depending on the configuration, that could be, you may need to replace those nozzles every couple years, and that could be, $1,000 to $1,500 to replace the nozzles and the nozzle ring. So that's kind of maybe on average you're looking at an $800 maintenance cost per year per unit. So that's something I would use as a budgetary estimate. Any odor treatment? I believe is that's what the question is. Yes, the system can be utilized. You can inject odor suppressants and other types of chemicals or organic material into the system to suppress odor. These systems, while they're designed for evaporation, they've been used for lots of different applications, including odor suppression, dust suppression. As we can imagine, we're launching droplets, creating droplets that can be used for different applications. So I'd say, yes, you can. But maybe if there's any other follow-up questions on specifically what odor suppressants or odor applications you're looking for, please follow up with me afterwards. Question, any impact of the presence of suspended solids or dissolved solids on EcoMister performance? Yeah, good question. So yes, there is with this type of technology, and it really, like I said before, it really does depend on the water type and what is in that water. With dissolved solids, generally the nozzles, and we can use different types of nozzles and different material types of the nozzles. We typically use a similar type of nozzle, but the materials we can select can be different. Dissolved solids are usually not an issue. We can handle very high concentrations of dissolved solids. So that's not really, as you get into suspended solids, we have a filter system on if the pumping system is provided by us, we provide a filtration system on it, and that helps pull out some of those solids or mitigate the risk of the solids entering the system. With suspended solids, you could have more potential for negative impacts on evaporation efficiency, I would say. But in general, we can handle decent suspended solids as well. It really just depends on the site, the water. We like to look at the water quality reports and advise on how that might impact the system in terms of performance and maintenance on it. So happy to answer more questions if there's some specific ones on a site or certain type of water that you're working with. Yeah, so good question. So produced water, oil and gas sector with high TPH and norms can be done with this technology. Yes, we've handled all sorts of water types, and again, it really depends on the local requirements and if there's permitting requirements for different types. I'd say that there's been applications where I don't think there's ever been applications where permitting hasn't been granted. If that's a requirement, but there might be certain conditions on what permitting might need for certain site locations. But yes, I'd say in most cases, yes, this type of water is fine, but it really depends on the concentration levels and whether they fall within the local permitting requirements, the regional permitting requirements. Again, we're trying to control these droplets and return contaminants back into the pond, but we're not really doing anything that a pond is not already doing, right? We're basically enhancing the evaporation process. The pond's already evaporating this water, and so it's just trying to manage what the expectations are and what the needs are for local permitting. And some sites, like I said, some of the energy customers in the U.S., they may pre-treat some of the water and knock some of the contaminants out before they evaporate it, and it really just depends on a site-by-site kind of evaluation. What are the long-term effects in the environment with turbine usage? I'm not totally clear on that question, so maybe you can follow up with a follow-up question, or maybe we can follow up offline as well. Just going to jump to the next one. How is the efficiency at the long time? As an example, what's the increase rate will be with the time? I'm not totally clear, but maybe stating that, over time, the efficiency, what's the efficiency impacted over time is maybe what's being asked here. Typically, those efficiency numbers, if the system's maintained properly, the efficiency numbers stay consistent. If the climate changes at certain sites, with people are talking about climate change and other things, if the climate changes, the evaporation rates will change with that, right? And seasonality you may have. That's why we like to use climate data that's pulled from multiple years, because we can then say over time, this is the average for this site. You might have good years and bad years. I'm not sure if that fully answers the question, so please feel free to follow up with me directly if you want more info. A lot of great questions here. This is great. For sandy weather, sandy water, shall we expect more solid accumulation with the pond? More frequent cleaning is required? Yeah, it's a good question. So if we're talking about sand in the water, we would typically design the system to have an intake that would likely pull from the top of the pond. So we're not sucking as much of the sand or the solids into the system. And more frequent cleaning, yes, might be required. So there might just be a different maintenance schedule for a system on a site like this. And it might mean that the nozzles need to be replaced more frequent, or we may change the material on the nozzles to accommodate the different solid content within the water. And hopefully, yeah, this question, I think it may follow up from before, how to control solids and droplets and norms. So especially salts. So yeah, so basically we can control the droplets first off by designing the droplet size for the type of water and for the site requirements. And then we can adjust droplet and control through automating the system. And what we typically use is VFDs, variable frequency drives, on our motors, on our pump motors and our fan motors, and that allows us to optimize for the site. Controlling the pump allows us to change droplet sizes live to accommodate for conditions. In really salty climates or salty water, the system can handle it. There's a couple other enhancers that we can utilize when there's high conductivity of the water as well, that basically help keep the solids suspended in the water. And they're basically like ionizers, and they charge the water particles. So there's things like that we can add into the system. And then there's just the control droplets with the salts. Like sites that have high salts and want to be spraying basically salt water into a containment area, they may want to put up some drift fencing or something like that if they're trying to harvest the salt and remove a lot of the water. So again, that's kind of an application by application evaluation that we would want to do with the customer. Yeah, so good question. So following up to the odor treatment, yeah, again, it does. It really depends on the wastewater and what's in the wastewater, and whether that water we can direct inject a suppressant in line with the system as it's running to help mitigate odor, or is there something that does there need to be a treatment that happens before the system is run? And again, that can all be evaluated as part of the cost benefit to other technologies. And if we can add, if we need to add a suppressant and still run the system, is that still more cost effective? Very likely it would be. But again, that needs to be looked at a site by site. other sites we found actually that, because we're evaporating and we're pumping water, there's some aeration that's occurring. We actually in some sites that have biological odors, we might actually be over time be able to help reduce the odor just naturally by helping it to oxygenate the water a bit more and allow for more natural breakdown of the materials, the organic materials in those odors. So again, it really does depend on the site and the water. But I'd say, looking at it on a case-by-case basis is really important. And yes, having wind speed control, having control of the system. If you've got if we're at a landfill and the leachate pond really smells, we're not typically seeing that we're increasing the smell by much. It's just the water smells, the material smells. It's just controlling the system, so it's keeping all those droplets inside of the containment area is really what needs to happen. Okay, perfect. Thank you for the note, Riaz. How effective is this technology with respect to produced and flowback water from hydraulic fracturing? Again, depending on the setup of how we're managing that water, if we're putting that into a pond, like a settling pond or storage pond, storage basin, can be very effective. But again, we need to look at what's in the specific the water that we're pumping at that site. But very effective at reducing water volumes, managing water volumes. And again, some sites manage it in different ways. So we'd want to look at the specific application, and we can run some estimates for that as well. But in general, it works. It can work quite well. Can we copy the slide pack? Yeah, I'll talk to Pooja and see if we can get something sent out after the presentation. Do you have floating units that look similar to the land-based unit you have shown in the presentation? Do you have a typical arrangement of a floating unit for understanding, like how much space to leave between two floating units, for example? Yes, we do have, they do look similar to the land-based units. We did basically remove the legs or the wheels or the trailer base. They basically get mounted onto, polyurethane dock. That's typically how they're done. Depending on the site, depending on the configuration, they're usually pointed in different directions on the float to maximize availability and limit, interruption of the plumes or interception of the plumes. But I think I can, probably if we can share quantities, I can share some more information with you after the presentation here. Is that it for questions? Which I think we went through quite a bit. I think that's it. I think you're muted there, Pooja.
Yeah, I think we had a really good round of question answer session with some really great and strong insights shared by you. Thank you so much, Sean, for all the valuable insights on the EcoMister Evaporator. Thank you all for attending today's webinar. Please note that we have another webinar on digital strategy for optimum oil production by our exhibitor Ozna from Russia in the next week on 8th of June at 10 a.m. Oman time. The details are available on our website www.omanexpo.com. We request you to register and attend the webinar. As mentioned by Sean, the presentation will be available in your email right after the session ends. Thank you so much, everyone, for attending. Thank you, Sean, for all the valuable insights. Thank you so much, and have a good day ahead.
Thank you, guys. Appreciate the time. Thank you.